Thank you. Thank you everybody for joining in person and online as well. So this is gonna be an event on overheating for residential assets. First of all, thank you to CIBSE for hosting the event. Gonna try to see if technology works. It does. Perfect. So first of all, for people who don't know about CIBSE Building Simulation, we're a group we're actually dealing with building simulation. We've been on for how many years, Darren? 15? No, 16, 17 years as a group? Yeah. Well, 14 then. For the last maybe 6 years, we'll be running the CIBSE Building Simulation Award. So we're celebrating teams that are working on building simulation projects, and we're also celebrating young modelers. So we've extended the deadline for submission, and this is in 2 weeks more or less time, so on the 30th of October, so you still have time. Please go ahead and submit, it's very important. And we'll be announcing the shortlisted people and the presentations and the Young Modeler Award at the Build to Perform event on the 29th of November. So our panelists, you can clearly see I'm not very good with the microphone. So the panelists, and they are on order of people who are actually speaking during the event. So Susie from Inkling, then Ben from Hilsham Moran, and Jack from Apex Acoustics. Do you want me to run down how the presentation is going to run, or do you want to do it? Presentation is going to run in terms of how we can structure. So I think at the beginning, we're going to start with the part 2, what it is about, the changes between this and CIBSE TM59. Then we're going to get a bit geeky and talk about openable windows. This is down to you, Ben, to do that. I know you love geekiness. And then we're going to talk about one of the biggest issues when it comes to overheating residential, which is acoustics. So the floor is yours, guys. I would probably say any questions you have, just keep them for the end. And any questions you have on the chat, just please post them and I'll just keep a record of them. Thank you.
Right, hello. Hopefully you can hear me at home as well. Hello, everybody in real life. This is novel. So yeah, my name's Susie Diamond. I'm a partner at Inkling. We're a building services, building physics consultancy. We offer a whole range of services. That's our plug. I'm doing the intro to Part O today, so I'm going to whiz through the basics of what is included in the building. Sorry, do I need to stand a bit closer? I'm going to do the intro to what's included in Part O, and then, yeah, the geeky bits we're going to pull out and investigate in a bit more detail. And we're focusing today on the stuff more commonly needed to be understood by the modelers, the people who are actually carrying out these assessments. So Part O, you may or may not know, came into force in, I can see it here, came into force in June this year. There are some transition arrangements, but essentially any project now going forward will need to comply. It applies to all new homes, including care homes, boarding schools, all student accommodation, and its primary objective is to reduce overheating risk in those buildings. It sets out 2 main routes to compliance. There's a simplified method, which is intended to be quicker and easier to apply. It's more prescriptive, which is often the trade-off, and the main focus within it is on glazing areas, and so setting maximum limits on glazing areas and minimum limits on free areas, so the ventilation provided. The alternative, and we'll cover these in a bit more detail going forward, is the dynamic thermal modelling method, so follows the CIBSE TM59 protocol. It does need more specialist modelling software and an experienced modeller to run that software, but it affords a lot more flexibility. It's more location specific, and we'll see there's a few other sort of key advantages that come with doing things that way. Obviously, it is potentially a lot more expensive to do those sort of assessments. There are a number of additional requirements within Part O that I think even as modelers it's really important to be aware of because they do have an impact on the modelling assessment. One of the key ones, and we're very fortunate to be joined by Jack Harvey-Clark today, is around noise. And there are acoustic limits set for bedrooms at night under Part O. And he will talk to you a bit more about what those exactly entail. But the understanding is that many UK sites are going to exceed those noise levels. They're not that noisy. And there are significant repercussions, because what the building reg says is that if those noise levels are exceeded in bedrooms, you need to, you can't exceed them essentially. So you need to close the windows, you need to do something else. And we'll see there's a hierarchy of potential solutions depending on the severity of that exceedance. And there's quite a lot of guidance out there, which again, Jack will point us to. So we'll be coming back to that. On top of the noise, there's additional requirements around security. So windows that are relied upon for nighttime ventilation need to be secure. So that's bedroom windows that are accessible. So ground floor in particular, any ground floor bedroom windows, you're going to need to pay extra attention to. The likely solutions will include fixed lockable louvered shutters, grills, railings and so forth. But again, as modelers, we'll need to take into account whether those are going to have an impact on the ventilation potential of those windows. So what does that do to the discharge coefficient and so forth? So we need to take those into account for windows affected. But it is just bedroom windows and predominantly. And I think it's during the day as well, because they're going to be fixed, aren't they? Another one, on top of all that, protection from falling. So with good reason, there are some additional safety requirements, although there's questionable why these are different to what's in Part K, which is traditionally where we keep all the health and safety parts of building regulations. So for some reason, these supersede Part K. There is a limit on how wide windows can open, and this includes ground floor windows as well. You need to measure from the inside face of the wall to the handle of the window, can't exceed 650 millimeters. Now, the window can technically open wider than that, but you can't include in the model or in any of your assessment an opening that would exceed that limit, because it's based on people falling out of the window as they open the window too wide or reach to close it. So again, well motivated, but it's a fiddly thing to apply, and we'll come back to that. I think Ben's going to cover that in a bit more detail, how we might go about that as modelers to make sure that we capture it for every window. And in addition, again, this doesn't so much affect the modelling, but is worth flagging up to clients, any sill heights that are lower than 1100 millimeters, and that's going to be quite a lot based on current designs. And this is upper floor windows, or where the inside to outside difference is more than 600 mil. Yeah, the sill height needs to be at least 1100 mil, or there is a tolerance of minus 100 mil if it's a means of escape, because which one is it? The fire regulations require means of escape to be lower than 1100. Oh, I keep forgetting the exact numbers. But anyway, there is a slight tolerance. So the house builders are, lobbied for it very hard. In addition, so guarding, you can use, so if you have got an opening lower than that, it needs to be guarded to make sure that 1100 is the sort of safe limit. So I need to rattle, I forgot to set my timer. The simplified method, as I said, it's not that simple. You have to assess every single unit in a scheme. There are two key requirements. There's a maximum limit on the glazing areas and a minimum limit on the free areas, which vary depending on the location of the site and whether it's cross ventilated and what orientation your most glazed facade face is, etc., etc. You also need to take quite a lot of detailed measurements for each unit and each window in each unit, and that includes the glazed area and the sash area, which is the pane of the window that opens, how big that is, the floor area of the room, the GIA for the whole house, and then etc., etc. But the good news, and shading, everything in London needs to have additional shading. This is under the simplified method, which could be external shutters, low G glass, or an overhang. But the good news is the Future Homes Hub have produced a spreadsheet, which is free to download, that will take you through that calc and sort of asks you step by step all the questions, and you fill it all in diligently, and then it spits out the answers. And that, as we'll come back to later, that has a little calculator that enables that does that 650 mil reach angle check. So you can use that to help feed into your dynamic model if you want to. And I advise that you might. The alternative to the simplified method, and that's what we're going to talk a bit more about today, is the dynamic thermal modelling method. So that's my bag. I'm a TAS modeller. I was one of the authors of TM59, so I'm quite embedded in it. The advantage of using this route through building regs is that you can assess a sample set of units, so you don't have to do every single one. And I've got a slide on how you might select that sample sensibly. It's based on CIBSE TM59. There's 2 criteria. You get results for every occupied room, so bedrooms, living rooms, kitchens, etc. And as a modeller, you should be providing a commentary on any spaces that don't immediately pass those criteria, on which criteria it fails, why that might be, what mitigations might be suitable under those circumstances to enable a pass. When it comes to selecting it, I realise I'm rabbiting, but we've got a lot to get through. When it comes to selecting a sample of units, the key thing is to select those that are likely to have the highest risk of overheating. You know, you're not going to get away with picking all the ones that are around on the north side of the building that are sort of right near the ground floor and really shaded. That's not cool. So ideally, you want to be picking one of each unit type, looking at units that have the most solar exposure, that have got the biggest glazing area, or have the least sort of shading from surrounding buildings or other features. Areas that might have constraints to window openings, so noise, pollution, whatever reasons you might not want to open windows, security on the ground floor. And there is a Good Homes Alliance, again, another of the things I've written, is a one-page tool for the Good Homes Alliance, which is free to download from their website, which just in one page kind of summarizes the key risk factors for overheating in homes. And if you're unfamiliar with what they are, a quick whiz through that might help you understand where in a scheme the key risks are, and then help you pick your set of units, flagging up more of those red flags. So other advantages of using the dynamic thermal modelling method are that you choose weather data local to the site, and as anyone who's explored a particular set of units and travelled them through various different CIBSE weather files will attest, outside of London is way easier to pass than inside of London. There's a really striking difference, and that's useful for sites that are well outside of London, but immediately causes an issue, particularly for Heathrow, which is the worst case weather file. Just for anyone who hasn't already picked that up, Heathrow is a real challenge. You do need to use the CIBSE 2020 high emissions 50th percentile DSY1 file. That's the key one that you need to pass against. So again, as modelers, you should be familiar with that and have access to that. And there is a spreadsheet that CIBSE have provided for the Part L that if you're in doubt about which is the best weather file to use, you put in the postcode and it tells you what the CIBSE location is. You can download that from their website. So advantages of the modelling method: natural ventilation, much more accurately reflected using the models. It's not perfect, but they do take into account cross ventilation, the shape of your windows, discharge coefficients, as we'll see, and the local weather file. So on a windier site, you'll get more advantage to opening your windows. Also enable you to include more design options like ceiling fans, which is one of the new ones. We're still kind of testing out how much impact they have, but potentially in real life, at least, adding a ceiling fan to a sweltering, particularly a single aspect room that's really struggling to get a breeze through, could be really beneficial to the occupants there and make them feel a lot more comfortable, even if the air temperature is still high. External shading devices of all manner of description we can add to our models. Mechanical ventilation and or cooling in various different guises can be included to model the benefits and the effects that those could have on the results. So quite a lot of options. In terms of differences between the original TM59, vanilla as we're trying to call it, and the Part O requirements, there are some changes, irritatingly, that they've made. Mostly around window openings, so that's now they've required that windows open gradually when internal temperatures exceed 22 degrees, windows start to open, and they're not fully open until internal temperatures above 26 degrees. They've required that bedroom windows are open all night if the bedroom exceeds 23 degrees at 11 p.m. And until recently, we couldn't actually do that in a lot of models. So I don't know how they tested it, but now that's been implemented in, I know TAS and IS have implemented that, so it's possible. It does some weird things to results, but you can sort of see the logic there. People are going to bed, they don't want to wake up in the night to alter the windows, but I think it's arguable that if you were hot in the night, you might get up and open the window. It's either way. But the really big hitter here is that the approved document does not allow you to include blinds or curtains in your model, and that historically, particularly in London sites, was one of the big last resort things that you could add in some internal blinds, and yes, you had to include them in the build, but they would help you pass your TM59 assessment. No longer. So this is going to be a challenge. I'm nearly finished. Whatever method you follow, simplified or dynamic, there are reporting requirements that need to go to builder control. The Future Homes Hub spreadsheet has a template inside it for the simplified method results, so that it helps you populate. But if you're using the dynamic modelling route, you need to complete a proper modelling report. There's a list of what needs to be included inside it, and that has to go to building control together with your results. So, which method? It's a balance. The simplified method does have some advantages, but what I'm finding as I'm applying it is that there's quite a narrow band with which you can comply. There's a real narrow sweet spot between having too much glazing and not enough free area, that it is quite challenging. So I think a lot of house builders are running their standard units through the simplified method and going, oh, it fails. Do I want to make loads of changes to it, or do I want to run it through the dynamic modelling method? Let's try the dynamic modelling method and see if we can get past there. Often they can. So I think there's a lot of work out there for modelers, which, could be a really good thing, but we're going to have to really get our act together, be consistent, do a really good job on these models and make sure that we're doing them right. So hence this talk today. So pros and cons to both, but I would argue that we're going to see a lot more modelling, and that's not just my bias. There are a lot of resources, and it's building. There's going to be more and more out there to help you. The Good Homes Alliance early stage tool that I mentioned before, free to download. CIBSE TM59 you can get from the CIBSE website. The Future Homes Hub guidance, I wrote with Julie Goffroy a couple of pieces for them that are, again, free to download, technical guidance that takes you the nitty-gritty, mostly the simplified method because it's for house builders, but it does cover TM59 as well, and all the detail of what you need to do. Jack's guidance, which he will come to later as well, on acoustic and how you measure the noise on site and how you respond to that. There are FAQs on the DLUC website, so where they've published the building regs. We're not convinced they're the questions most frequently asked, but they do augment some of the guidance in the approved document, which is very scant. And I've written a number of blogs now for the Inkling website, so check us out. There will be a fourth coming quite soon with some of the content from today. Oh, little animated one coming in at the end. Right, so I'm going to hand over now to Ben, who's going to get busy with the science stuff. Thank you very much.
Right, thank you, Susie. So yeah, I'm going to cover a bit of a more sciencey bit. Quick bit on Hilson Ram. We're a multi-disc engineering practice, and we've got a long history of building simulation, 20 years, and I've been there for most of them for my sins. So what I want to cover today is, I think one of the important bits is how we model the openings in our buildings, how we model the windows, and how we get some consistency, because there are many approaches you could take. There are many inputs in the modelling tools, and there are many ways that you could come up with different answers, whether they're right or wrong. And I think it's important as a community that we try and come up with either a standardised approach or approach that we can all sort of agree on. So I'm going to go through some of that and sort of give our collective opinion. Me, Susie, and Jack have sort of been mulling this over for a week or two at least, and trying to come up with what we think is a sort of sensible way forward. So the first thing to look at is the fact that there are many definitions for what we call the opening bit of the window. So we have free area, equivalent area, and effective area are the sort of three key terms. And depending where you look, you'll get different definitions, even between the building regulations. So even between Part O and Part F, there's differences. So it's, and if you look wider, there's many. There's papers written on this subject, so it's very confusing. So as a community, we want to really sort of work out how we should best approach this. So I'm going to quickly sort of spin through these and sort of outline them, and then sort of go through what we think is a sensible approach for our modelling inputs. Free area is literally the whole. It's not the bit around it. It's the, you know, when you open the window, it's the whole bit. And that's very often difficult. People define it different ways, but you know, and also the thing to think about is it is the whole. So when you open a window, so that image on the bottom right, the sash area, when you open that, you'll have some frame that overhangs the hole. So when you are entering that into your model, what do you put? Because your window in your model might be the pane and the frame, and the opening bit might just be the pane bit. So you have to think carefully how we input the data into the model to correctly have free area. So the next thing we look at is effective area. So effective area is that free area times the discharge coefficient. So discharge coefficient is just a way at looking at the aerodynamic interference that all the bits of the window contribute to air coming in through that hole. So whether it's like this, a top hung window, side hung, etc., and they will perform differently for different types of window. So the discharge coefficient has to be calculated for each window type, for each opening angle setting for your window. So you can't, it's very difficult to, on the face of it, work out what that discharge coefficient might be. So you have to do it via experiment. And from that graph, you can see obviously it varies for different opening angles, for different ratios of width and height of that window. They all tend to, so when you get to a fully open hole, they all tend to a discharge coefficient of about 0.61 is the sort of accepted norm around that value. So, you know, whether that's a square or a rectangle or even a circular hole, they will tend to that sort of value. But as you move away from that, it varies, and you need to come at that by experimentation. So equivalent area is just an extension of effective area. So you're just dividing your effective area by that maximum discharge coefficient of 0.61. So, but an interesting to point out is that part O actually says, when it says free area, it's actually talking about equivalent area. So it's confusing even within part O what free area actually means. So we need to sort of generate some clarity about what terminologies we're using where and what they actually mean and what value you use for that in your model. So there's a great little tool on the government website under the Building Bulletin 101 schools calculation tool. It's a little coefficient calculator. So you put in the width and height. So the yellow ones, green, depends which color. The yellow ones at the top are your entry boxes. So width and height of your opening, the opening angle of your window. Obviously, if it's a sliding window or something like that, you'd put 90 degrees. It's fully open, and that generates your equivalent, your effective area, and your free area, which is obviously just width and height, but it also calculates the discharge coefficient for you. So in discussion, we've sort of come to the conclusion that actually free area and discharge coefficient are probably the most pertinent figures to use in your models, because equivalent area and effective area can be misinterpreted, whereas this calculator will, free area is fairly easy to measure. You just measure the size of the opening, and the discharge coefficient is spat out from this. They can say this tool is a little bit, I wouldn't say it's basic. So there is work going on, and I'll come on to that to improve this to get better accuracy. So, and the other advantage is if you use discharge coefficient and free area, that is common in all three modelling tools that you can use this. So TAS, IES, Design Builder all have discharge coefficient. They all call it discharge coefficient. They all have something which is effectively the free area. TAS calls it a factor. IES calls it an openable area. Design Builder calls it glazing area opens, but effectively that's your free area. So most of the tools have other options, but again, there is use the other stuff behind that. So it's, you know, I know in IES there's many options. You can select different window types, and there's probably good research behind all that, but it's not quite as transparent as this. So again, in terms of consistency and variation between modelling tools and stuff, you know, we think that having an openable area and discharge coefficient is the most sort of transparent way of doing that. And I said there was some research going on. So Patrick Sharp and others at Nottingham, Ben Jones and Chris Idden and others who are known to the building simulation community have published an excellent paper on this. So looking at developing a better model to look at window opening. So they've taken the standard BB101 calculator I've just shown you, and they've done some other physical tests and some modelling to look at that, and they've come up with this statistical effective area modelling tool, SEAM, which is getting much better correlation, much less error in its prediction of the window openings. Now, at the moment, this is an official tool, so you know, unlike the BB1 calculator, which is on the government website, and this tool isn't released yet, but obviously, if we have something that's a bit more accurate, it'd be great to get that officially stamped and so we can use it for. But that paper, excellent paper. If you're interested in this, that paper is an excellent paper and goes into all this detail. And then, yes, to pick up on Susie is, yeah, we don't want people falling out of windows. There is that 650 limit. So when you're doing your calculations, make sure you take account of that. Susie also mentioned in the Future Homes Hub, there is a spreadsheet which also calculates discharge coefficient for you. So it takes in all those factors, yeah, as in again, making sure that 650 reach is complied with, and it works out for both day and nighttime conditions. So again, that's another resource. You want to double check you've calculated discharge coefficient correctly from the BB101. It's a similar tool. It will also help you look at that. And then Jack will cover this in a bit more detail, but obviously noise exceedance, you can do your modelling with your window openings, but you still got to comply with noise criteria. So, you know, nighttime is the key one. Make sure you talk to your acoustic consultant and work with them to make sure, you know, you're in tandem. You know, I think gone are the days where you could do overheating assessment with the windows open, and you could submit your acoustic report with the windows closed, and they would both get ticked off, and everybody would be happy. Most of the local authorities are wise to that, and you know, obviously that's not the sort of practice we want to be encouraging anyway. So we want to do all that, and yeah, just looking through the sort of hierarchy of stuff. So passive first, adding additional mechanical vent where you can't quite get that, and then resorting to comfort cooling as a last resort. So this is just a quick example of a building we've been working on where we've done an extension to the top 3 floors of the building. It's in central London, surrounded by 2 roads, pretty noisy, busy roads. So we have a nice free area we can get them to pass, but as we back off that free area to get to something that is close to getting through the noise criteria, pretty much we start failing almost all the units. So it then becomes a battle about why don't we just go to full comfort cooling, and that's the sort of thing we want to try and avoid. If we do have to go to comfort cooling, and what we've been looking at recently in another project is, can we offset some of that heat? So in this case, we're using the rejected heat from the space. So we're taking the heat from the space, we're using that to heat our hot water. So, which is better than dumping it to atmosphere. So you actually you're getting a benefit. Again, that sort of area in building regs is a bit unclear about how that crosses over, because you're taking useful heat from the flat and you're translating it into your hot water. Hot water is always needed. The things to look at here, obviously, we've used a more realistic hot water profile than you'll see in your NCM internal conditions, and also matching the loads. But also, if you're using the TM59 internal gains, which were designed for stress testing a passive design, that might not be appropriate for sizing your hot water, because it might give you an overestimation of the hot water load you might derive from that shift of heat from the space to your hot water. So, but always the process you should go through is, test that passively first, see how far you can push the apartment before you start moving towards, going to comfort cooling or something like this, where you're trying to sort of load shift heat away from the space into another use. I'll now hand over to Jeff.
Hi, thank you, Susie and Ben, for the invitation here as well. So, my name is Jack Harvey-Clark. I'm the founder of Apex Acoustics. We started just me. We're now 25 people. We do acoustics and air quality. Offices in London, Midlands, North East and Manchester. And this question of noise and overheating and noise and ventilation is something that I started really nearly a decade ago when I wrote a conference paper about it. Because as Ben mentioned, we used to do acoustics entirely separately from how ventilation was considered or mitigating overheating. And trying to integrate those things together is a difficult and painful journey that we're all on now together. So not to share the pain, but to share the difficulties that we're facing. One of the key difficulties is how we describe the performance of the facade. Ben's been talking about the openings for the ventilation performance, and I'm going to talk about how we understand those openings for acoustic performance. And you'll see, hopefully, why it's so important that we make the same assumptions about what the facade is, how it's performing, what an open window is, because it's not easy to understand. So we get information on approved document O from the approved document itself, but that is partially superseded by the FAQs, which contradict some of the information in the approved document. So Susie usefully wrote and others maybe as well, but mostly, the Future Homes Hub guidance. And to contribute to this, we've written, a group of us in the acoustics industry, a guide to demonstrating compliance with the acoustic requirements of approved document O. And we needed to do this because there's a very little bit of information about acoustics in the approved document, and it could be interpreted in a wide range of ways. And we want everybody to be on the same page, doing it consistently, because that's better for all of us, really, as an industry. So in the approved document, it's only got 3 paragraphs about noise. And the first one says where you might want to consider noise. And as an example of that is if noise is considered in planning. Because what's happening here is a little bit of noise is taken out of planning. So noise in bedrooms at night, while you're mitigating overheating, is now under building regs. But noise in bedrooms in the daytime and noise in other rooms, when you're providing ventilation or when you're mitigating overheating, is still under planning. So this is going to cause a lot of confusion for building control and environmental health. We'll have to live with that. This is the key paragraph in the approved documents. If noise exceeds these limits, then we can't assume that windows are open to mitigate overheating. So these numbers, 40 dB as an average over the night time and 55 dB LAF max, not exceeded more than 10 times, are 10 dB higher than the normal levels that we design for with windows closed. So this represents a tolerance on the normal levels to enable natural ventilation to mitigate overheating. Otherwise, if we didn't have that tolerance, there would be nowhere, very, very few places we could rely on opening windows to mitigate overheating. One of the things that we're saying in the guide is that we want to agree we can demonstrate compliance by design. Nobody wants to rely on testing the building when it's completed to demonstrate compliance, because that invokes a whole lot of other risks. Contractors hate doing that, of course, as well. But in the same way, your thermal model, you demonstrate compliance by design. So we want to demonstrate compliance with the acoustics by design as well. We talk about things like the types of noise that are considered. You don't want to fail the building regulations because your neighbour's dog barks. So we rule out things like natural sounds. So the sounds from the weather, the wind and the rain, sounds from wild animals. We rule those things out, and it's just the anthropogenic sources of noise. Noise from people and people's activity, which is mostly transportation, but it could also be industrial sources. As Ben mentioned, everywhere in the approved document where it says minimum free area, it means minimum equivalent area, because you have to calculate the equivalent area of your partially open window, and that has to be more than the minimum free area. So it would be much clearer if they just said minimum equivalent area rather than minimum free area. But this is clarified in one of the FAQs. They really do mean equivalent area. So their definition of free area in approved document O is the definition of equivalent area. So don't confuse the width times height of the opening with the free area that you have to achieve in approved document O. So there is a link to the discharge coefficient calculator that Ben was talking about is linked in the approved document. So it is an official resource, if you like, for doing this. You don't have to find it yourself. The link's there. And so that's a little spreadsheet because you can't calculate the equivalent area by measuring the size of your window. You have to calculate it from the empirical data, as Ben mentioned. So how are we going to understand this open area for its acoustic performance? So we've got a window open to some number of degrees. We can calculate its equivalent area, so its ventilation performance, and we want to calculate its acoustic performance as well. So there is a little bit of test data available out there, but not very much for partially open windows. So we've invented another term, the acoustic open area. I'm sorry, bear with me, it's worth it, because if we didn't do that, this would be much, much trickier. So the acoustic open area is the smaller, the way we're describing it, of either the area of these triangle, the rectangle and the triangles, if the window's open to a small extent, or the width times height. So this is considering the acoustic open area as an element with 0 sound reduction index. There's very good reasons for doing that, which I'll show you. So this standard tells us how we calculate the sound ingress through an element from the sound outside. And some details in the annex that says for openings, you can make these assumptions. And what this means is that's an element with 0 sound reduction. So this is a very useful note in the standard that we're making use of here. That's the equation for calculating the noise through an element. And the advantage of doing this, is that if we make assumptions about the relationship between the acoustic free area and the floor area, then those variables drop out of the equation. And if we make an assumption about the room height, then all the variables drop out, and the level difference from inside to outside is simply a function of the acoustic free area divided by the floor area. If your acoustic free area is 5% of the floor area, which is probably what you need to get an equivalent area of 4% when your window's open 60 degrees, the level difference between outside and inside is 9 dB, irrespective of your room size. So you don't have to do a different calculation for every different size room. That's the advantage of doing this. So in the simplified method, we can say then the difference between the inside and the outside level, it's reasonable to assume 9 dB. So we can measure the outside noise level, or we can model the outside noise level and work out if the simplified method can be used acoustically based on that opening. So that was a bit of a journey. So that's for moderate risk areas. In London, because you have to have 13% of the floor area to be the equivalent area, that level difference between outside and inside drops to 4 dB. So it's noisier, and if you're trying to use the simplified method, you have to assume a smaller level difference to outside to inside. So there's even less chance the simplified method is going to work at all. So we can use the spreadsheet on the government website to calculate equivalent area based on angle of opening. So this is for a window with a 1-to-1 aspect ratio. You get slightly different graph shapes if the aspect ratio is different. So what this shows here, so this is the equivalent area, the angle of opening on the bottom and the area on the side. So the orange line shows how the equivalent area increases with open angle, and the blue line shows how the acoustic open area increases until it's slightly over 30 degrees. So when the window is open 30 degrees, if it has a 1-to-1 aspect ratio, the area of that blue triangle, blue rectangle and the blue triangles on the side is equal to the width times height. It might have been a smaller angle than you might have thought, but so we're saying the acoustic open area can't be any bigger. Your area that's open for the sound, it can't be any bigger than the width times height. So that brings us to these numbers for moderate risk locations everywhere outside London for using the simplified method. So this is an acoustic constraint to using the simplified method, these noise levels. I'll skip over that bit. There's a question then, to how many properties is this going to affect? I'm not going to be able to rely on using the simplified method because of the noise. So the last time there was a big national noise incidence study was about 20 years ago, where noise was measured outside people's houses all over the country. And they characterized those types of locations as rural, semi-rural, urban, suburban, and just think how many people are affected by what levels of noise. Lots and lots of graphs, but one of them looks like this. So at 49 dB for night, you can see that somewhere between 30 and 40% of people are exposed to higher noise levels than that at night. This means that more than 30% of existing properties would not comply with using the simplified method because of the noise. So almost everywhere, if you're on a site that's exposed to any sort of noise, the simplified method is not going to be feasible because of the extent of opening that you have to assume. So what the FAQs allow us to do is assume that the window is partially open at night. So this is a contradiction to what it says in the approved document. In the approved document, it says if you're doing dynamic thermal modelling, assume the windows are fully open. And rather than change the approved document, they just issued an FAQ which says actually you can model the windows as partially open at night. So this is vital for the noise because you often, in many locations and for many designs, you don't need that bigger open area at night. So the simplified method is meant to be a robust tool, but if the overheating risk isn't that big, a much smaller window opening at night can be sufficient to mitigate overheating, because obviously you need much less airflow at night to mitigate overheating than you do in the day. We can calculate the level difference from outside to inside you get using the acoustic open area. So this graph is showing the level difference across here. So it starts at this point with the simplified method. So this is a level difference of 9 dB when, in this example, it's a 20 square meter room with a window that's 1 meter square. So that's 5% of the floor area. So the discharge coefficient is about 0.64 when it's fully open. Oh, sorry, when it's open to 30, just over 30 degrees. So this is the opening angle on this axis in green. So this is the opening angle here, and the equivalent area is shown in the blue line here. So as you close the window, then the level difference from outside to inside increases as you move across to the right, and the equivalent area decreases. So the ventilation performance of your window decreases, which is what you would imagine. But rather than equivalent area being the exchange token between us acousticians and you thermal modelers, we think discharge coefficient might be better. So this is exactly the same information, but with discharge coefficient on the left-hand side. And this is because your models ask you for width times height of the opening and the discharge coefficient. So if we tell you the discharge coefficient, this is based on an assumption about the angle of opening of a window. You can put that in your models, and then we're making an assumption about the sound insulation performance, and you're making a consistent assumption about the ventilation performance of that window. So that was what the painful journey was to get to. I hope that's feels like a relief, maybe. So what do we do if we can't use the simplified method? So that at those noise levels, if the noise is less than that, you can use the simplified method if you want, but you don't have to, of course, but there's no noise constraints to using the simplified method. So above those noise levels, you need to use the graph I showed you in the previous slide with TM59 to investigate whether a reduced opening at night allows sufficient airflow to mitigate overheating and complies with the noise level limits. So there's what I call a window of opportunity there to still rely on opening windows. Above that, if the noise level and so what I should say there, so one of the responses to that, one of the design responses, instead of thinking, oh, my model's telling me it's failed, one of the design responses is to mitigate the overheating risk so that you need less airflow to mitigate overheating. So nothing to do with the noise or the airflow performance, but the other aspects of the design. So that is another way in which you might get the limit on or the constraint on the opening area to work thermally. The only other option to use passive means or natural ventilation then is to use attenuated openings or to attenuate the noise on the facade somehow. And I've got some examples about what they might be. Otherwise, of course, you're moving into mechanical ventilation or last resort, obviously mechanical. So we've spent quite a lot of time gathering evidence on passive attenuated openings from research around the world. And I'll give you, this is probably a bit optimistic, actually, the numbers on this slide, that the opportunities aren't as good as they look here, I now think. So there's some things like this that are called plenum windows. This is Danish research in response to the Danish regulations, where they have to have 0.35 square meters of what they call free area. So this gives you much better sound insulation, but you can see, as you know from the open areas you need, this is very unlikely to be enough to mitigate overheating. So unlikely to be a useful solution here. These type of designs, you might have come across the Hafen City windows. They're a German design, so they are designed in response to the German regulations, which I think say you have to be able to open the window 100 millimeters. So they're two sets of windows, and you can get a convoluted air path between them. So you get very good sound insulation, but you get very little airflow. So again, they're unlikely to be a solution to mitigate overheating here, whilst meeting TM59. So when I say they're unlikely to work alone, if you put them together with a mechanical extract fan or something like that, these types of things could be the air inlet path, or you could just be having an attenuated vent, would be a simpler way of doing that if you have mechanical extract ventilation, for example. This is a similar type of arrangement. So this was developed in Hong Kong for a public housing program, and you only get a small acoustic advantage, and they don't work that well for ventilation. So the answer is it's very difficult to do anything, basically, better than an open window that allows more airflow but doesn't let the noise in. You can use balconies to some extent. You have to be careful you don't make the sound on the facade worse by reflecting sound back onto it. So I'm not sure there's many examples of this ever being done in practice yet, but theoretically it's possible. So you need sound absorbent materials on your balcony soffit. Basically, that's what I've never actually seen that in practice. where you can start designing your balconies like this to have a convoluted air path through large openings to let the air through. But then you're starting to design your whole facade around the attenuated airflow. Now, on some designs that might be appropriate, but often that's not really the job that we're asked to do. So attenuated vents might have a role, and this is an example of one that was designed and built before TM59 was written, or designed before TM59 was written and built after it. But so that section of the window reveal has an attenuated vent behind it, and inside the room it looks like that. So it's in part of the wall. So this attenuated vent sounds like it might be a simple thing, but it's got a damper externally, which when it's closed, it needs to maintain the air tightness and the thermal envelope of the external wall. When it's open, it needs to let the air through, but attenuate the noise. So there's an electrically operated damper and then an attenuator. Because of that, the equivalent area of things like this tends to be about 1/5 of the physical size of it. So that's like having a window that's 1/5 of the size of that unit, where you think, well, that's not going to mitigate my overheating, is it? Very well. It might be enough to mitigate overheating at night, because you probably need less ventilation, well, you will need less ventilation at night. So this wouldn't pass TM59, I don't think, for the daytime operation. And it's been built, it's got external solar shading as well. So the conclusions that there's got very significant constraints from noise to using opening windows. You need to understand them early on, and you need a toolbox of options and approaches. And it's vital that we talk the same language for the opening. Who knew that an opening window was such a complicated thing to describe? We need strong collaboration between our disciplines. And we need this consistent description of the facade opening. We need to, although this is a building regulation requirement, obviously people need to know about this pre-planning because it affects the facade design. So I hope that wasn't too painful. Not too much acoustics in there.
Thank you all. So there are some questions that came from the chat, but before I go to that, I have a very open-ended generic question that I want to ask. So I think with last summer, with these extreme temperatures we actually have seen, the heat waves, I think these kind of regulations are important or essential. So my question is, do we think that Part O is more difficult compared to TM59? Do we think it's going towards the right way? And then probably a difficult question as well to respond, but do we think the building regulation guys are ready to receive all these reports from us? Do they know how to review them? I don't know, Ben, Susie, whoever wants to take this one.
Yeah, no, good question. I think the Part O version of TM59 will be harder, mostly because of the blinds, but also to do with the window opening regimes and the sort of strictness on those. I don't think there's a massive difference, but the blinds do make, it's that crunch bit, whereas previously TM59 was best practice, and if there was just 1 or 2 hours over the limit at the end of the assessment, then you could sort of make a call and say to the client, look, you know, we've done everything we can, it's just 1 or 2 hours in these units, it's probably not that big a deal. We can't do that with building regs, you have to comply. It's a end of, must pass. I did discuss this with DLUC and they were adamant. So I think that's going to be the challenge, and particularly for some of the London weather files, like I said. In terms of whether building control are ready, who knows? I mean, I've not spoken to any of them. I'm waiting for the calls when they're, I don't know, we'll see. We'll see. But I think one thing to be aware of is the buck does not stop with building control absolutely anymore. The Building Safety Act has been approved by Parliament, and that puts the responsibility squarely on the designers. So just complying, you know, sign off from building control is good, but it doesn't get you out of jail if your calcs are wrong. You're still liable. So you do need to, the onus is on us to make sure our calcs are right. And that's a change. That is a change that we need to be aware of. Does that answer your question? Okay. Hello, people at home.
Just to preempt your question, we're recording this session, so it's going to go online on YouTube from CIBSE if you want to revisit or anything like that. Somebody's asking a question in terms of future weather files and what we're doing them and how we're using them. I don't know if you, Ben or Susie, you want to talk about them.
Under Part O, there's no requirement to look at future weather files. I think a lot of clients, once we get our heads around it properly and are used to it, I think it would be sensible to start considering whether buildings also comply under future weather data and what mitigations might be planned in for the future to enable them to do so. But no, it's not a requirement. Does anyone in the room have any questions?
Anybody?
Go.
Hello. Yes. Similar question to the future weather files, but also based on the acoustics, because maybe there are more electric cars. So are we also thinking on reducing the acoustic limit or maybe the outdoor noise levels?
Yeah, that's a good question. So I think you mean because we all move to electric vehicles, will it actually get quieter? So how do we account for that? It'll actually take quite a long time before it gets much quieter. And when cars are moving more than about 30 miles an hour, more of the noise comes from the tyres and the wind over the body of the car than it does the engine. So faster moving traffic won't get much quieter, but the smaller streets where cars are moving more slowly will get quieter, but it will take quite a long time because you need very high proportion of electric vehicles before you see a significant noise drop. So we're not accounting for that at the minute.
I'm going to alternate from the audience to here and then back. So one question probably that Ben would like to take, because I know you love a QA, a good QA. So the question is there a plan to evaluate the quality of the simulated models and how to ensure the results are meaningful and representative of the actual building?
Yeah, I think the issues there, unlike with Part L at the moment, if you want to do an EPC or submit a Part L, you need to be registered through CIBSE or an approved assessor, and you need to keep up your CPD as, you need to have done the right modelling exams and test with the right software houses. With this, there isn't anything like that in place at the moment. Obviously, CIBSE are offering training courses on Part O, but there's not quite the same level of analysis and checking as Part L. So I think that's something that may come in time. I don't, and yeah, or there may be some certification through CIBSE.
Hi, Dan. Thanks very much for your talks. Darren, for Chair of the Building Simulation Group, I'm going to ask a simulation question. If you want to maximise your ventilation, you ideally want to get your discharge coefficient up towards about 0.6, being an orifice, simple orifice. And if you do anything, if you're applying, there's a lot of schematics of different types, side hung, top hung, but anything atypical, and you showed an acoustic vent there with dampers, you might not have the data to pull it into the calculators. You might have on the one side something on the acoustics, on the other side a discharge coefficient, but quite often you may not get the ensemble of both if you've got insect meshes or something like that added to it as well. So what we've done before is pull it into a CFD model, component level CFD model, where you've got the actual geometry, if it's an attenuator or something like that, you put a pressure difference across it, a number of pressure differences, get your pressure flow curves and your discharge coefficient pops out. And then you can sort of zoom in on the geometry, see where you get detailed separations, energy dissipation, and help design the attenuator so you maximise your flow. So I get that in terms of the fluid side, but in terms of the acoustic side, can you take that same geometry into, I believe it's boundary element models, and quite simply do the same sort of thing? What is the process of setting up a model within the acoustic side so that you get the data that you need?
So can we design better acoustic vents by modelling them? Unfortunately, it's not that easy. and you have to build them and test them. So you can't, you need test data. Acoustic modelling of things like that is, I mean, that's what the vent manufacturers do, but they still build them and test them to see if it actually works. So you can't design better vents on a building like that. That's what the vent manufacturers do, but they would always test them. I mean, they are, and the ones who are making vents for these sorts of applications are doing both the airflow and the acoustic tests. So that data does exist.
As you're actually standing, just pick up the last question. I think the question we've been often been asked for when we like working with design teams, and is like, in worst case scenario, can we compromise noise against overheating? And you know, what's the result of that? Well, any of you want to take that question? It's quite controversial.
I did read a paper a while back saying, you know, obviously your brain, if you live in a noisy environment, eventually your brain ignores certain noises, but apparently it still has an equivalent psychological effect. So living in a noisy environment, your brain switches it off, but it still disrupts you at a deeper psychological level, is how I understand it. So the fact that people get used to noisy environments still doesn't mean that it's better for that they are as well adjusted, or you know, they get the same quality of sleep as someone who, you know, lives out in the country where all they can hear is, you know, sheep and that sort of thing. I don't know what you've read, Jack.
When you look at the adverse impacts from noise, the biggest impact is sleep disturbance by a long way, and the next biggest impact is annoyance. And about 10 times smaller impacts are the physiological impacts, the effects of noise, because it increases your heart rate. So if you have any sort of cardiovascular disease, it increases your cardiovascular risk. But those risks and those impacts and effects are all much smaller than sleep disturbance and annoyance. And yes, people do get habituated, certainly. If you're used to living in the city and you go and try and sleep in the countryside where it's quiet, you can't sleep because it's too quiet, and vice versa. If you go out of your normal environment, it's disorientating. And sound is it's our early warning system. It's about keeping us safe and it's protection. So it's about danger. That's why you can't switch your ears off. You can't close your ears. You're always being alert to danger. And if you're in a different type of environment, it takes you a while to get used to it and feel safe again, essentially. Yes, you do get habituated, but at the sorts of levels that we're looking at, these are based on the evidence from large epidemiological studies that show these and this is where people have put, World Health Organization have put thresholds in as to where, you know, people shouldn't have to be exposed to higher levels of noise. But it's a very interesting question, because it's about, to what extent do we prioritize acoustic comfort over sustainable designs? How do we find that balance? Which I think is...
I have one thing to come back. I mean, the difference in noise and heat, people don't die from too much noise, generally. I mean, if it's too hot and you have health conditions, that can be a mortal danger. Unless someone's playing death metal for 18 hours a day, it's probably not going to kill you.
Yeah, no, I completely agree. And in the moment, you'll prioritize your thermal comfort over your acoustic comfort, probably. But the noise is the second biggest burden of environmental disease after air quality. Most people don't realise. And so it does have a big adverse impact on many, many people. It's a big burden. It's a big health burden, although people might not actually die.
Hi, I just wanted to ask, how do you account in your calculation for location of the property, like geographical location? So where in the calculations you say, okay, this is the noisy area, or I mean, the flats could be located in London, but it could be, I don't know, facing the courtyard of the building, which is not as noisy as if it facing the busy road, or maybe if you live in the ground floor, it will be noisier than on the top floor. I mean, how do you, because we've been talking about the room areas and areas of opening, but how do you integrate this factor into your calculations? Surely that's the most important factor, I would imagine. So I don't know.
Absolutely, yes. So we would normally measure the noise, do a noise survey, and then model the impact on the building. So we'd look at the variation of noise impact on different facades and at different heights.
So how do we know?
Read his report.
How do you? Yeah. So then we'll.
Right. It is there in the calculation.
Yes, and then we would say for this part of, so for this part of the facade, the maximum discharge coefficient with a window of this size would be this number. We've divided up into bits, but it is complicated because you're overlaying a varying noise impact on different aspects, and you've obviously got different overheating risk on different aspects. So you've got two different variables which aren't connected. And
Yeah, no, exactly what Jack was saying, but you're right, and it's understanding which facades and which parts of the building are affected by those noise issues, because it may well not be the entire site. It may well be one corner of it or one facade or those bits nearest the road, and being able to pick up on that really early stage. So you need an acoustic assessment really early on, and then you need to look at the site planning and ideally be looking at things like locating bedrooms away from those noisy facades, the problematic-y spaces, and designing the site so that passively you're making sure that the bedrooms are in the quieter spaces so that you're not having to put any limits on the bedroom windows and everyone's happy. But obviously there may be sites that have noise coming from all around, or single aspect flats that cannot be reoriented because of the constraints of the site. So that, yeah, that's when you need to up it a level. You should be asking for it, yes.
So I should be asking for acoustics.
Yeah. Are any units on the site affected and exceeding the noise criteria in Part O? And then you'll get a report with pretty coloured maps on all the facades telling you what you can do where. Yeah.
Thank you. Telchinelis from Finch Consulting. So even though I'm a noise consultant, I've been talking about this issue for over a decade now. With all the, I'll call you overheaters. And they've all been telling me for many years, and now they've confirmed that, yes, this is it, especially for London, they can't really make it work with passive means. And active means, either extra additional mechanical ventilation or comfort cooling will have to be the norm. However, if you put the systems in, they also create noise. Usually there's a fan moving and they create noise. So we have the new approved document F that was released with all of these approved documents in June, where now we have a noise limit for mechanical ventilation, for background ventilation, but we don't seem to have one for active systems that are there to prevent overheating. So what I can see happening is you guys suggesting mechanical means of comfort cooling, which are too noisy, and then people will just switch them off, and then, nothing is going to work. So who's going to set some kind of criteria for that, noise criteria for the active means of comfort cooling?
We have done that, or we've just referred to the CIBSE guidance for those noise criteria. Yeah, because I think that's one where that slips through the net, doesn't it? Because approved document F has, as you say, noise guidelines for whole dwelling ventilation and extract ventilation, but there aren't really any links to noise levels for the services to mitigate overheating.
Yeah, it's not in the building regs. So
it's not in the building.
What's building control going to do if we put in an active means that does 50 dB? They're just going to sign it off.
Yeah, it's not controlled under building regs,
right.
But there is CIBSE guidance on that. So as a designer, depends what you think your responsibility is to advise on.
Oh, yeah, well, I'll tell them, yeah, to put all that in ranges, but who's going to listen?
Well, that's we can only, as consultants, we can only give good advice, can't we? We don't build the buildings. So.
Hi, I have a question as a practitioner. So I was lucky enough to be involved in several Part O related residential modeling so far. And I have a question, because especially in London, with a lot of acoustic constraints, it's like incredibly difficult to make them pass. And I'm not even mentioning the simplified method 15% opening, or 18, how is it able to have this air movement inside the space? It's almost impossible. And daylight, I'm not going there. Talking about the dynamic modeling, it's quite challenging to be able with, especially the profiles, and not internal blinds, the other change, about the profiles related to the 22 to 26 degrees and 23 at night, to be able to have openable windows that provide adequate ventilation. Because people are adapted. So if you go in the Mediterranean region, for example, and you tell them that I'm closing my window to 26 degrees, they will laugh. Sorry for that, but I mean, for them, 26 is nothing. So, and I believe that humans generally adapt. So in London, with climate change, people will adjust. We experienced it last summer. So this is one of constraints that I have noticed, that it impacts the simulations. And I'm wondering, so it's more like a discussion. I'm wondering what will be the actual effect of having acoustic constraints. So I completely understand that. And actually, going to Ava, I will question, what about the living spaces? Or now that we're working from home, what happens if you're working and you have a busy road next to you, which is not part of the guide? And thank God, if we have to do that all day, then nothing will pass. If we're realistic, nothing will pass if we apply acoustic constraints to every space. But what about having all of these constraints and make it pass passively? And from my experience, a lot of challenging bedrooms, they will pass with double speed ventilation. So if we try to avoid active cooling, it's double speed ventilation the way forward, at least in my experience so far. And then we are reaching active cooling, which we all try to avoid because it's energy.
Yeah.
And I'm not even talking about operational energy and carbon and all of these additional items that we'll bring to the scheme. I'm talking about construction costs. I'm talking about the actual living cost with the bills that are going high as crazy.
Okay, there's a few things.
Yeah, I'm sorry. I'm sorry. We're going to say the discussion
well,
more.
I think there are some things to say on that. Where do we start? So in terms of mechanical cooling, I totally with you on that, and I think it makes clear in the regulation, actually, although it doesn't do it very well, that it's supposed to be the last resort. But so my view on this is that best practice would look like where noise constraints are limiting your ability to open windows freely, you would run the TM59, and I would run it with the windows open to demonstrate that were I to open the windows, it would pass, so it would be reasonable. And then I would close the windows and size the cooling based on the nighttime cooling load in order to achieve that comfort at night. Now that's going to be a lot smaller than sizing the cooling on the daytime overheating load. So I think whatever cooling goes in should be modest and should be there for that purpose and be clear that that's what it's there for and that it's not full comfort cooling. So that's one way. And then also, if you choose not to put the cooling on because you hate comfort cooling, you have the option to deal with the noise or to do other ways and open your windows, and your home should be comfortable in that way. Now, you raised a point at the beginning, cycle backwards, about adaptive comfort. Yes, so the issue with TM59 is that criterion 1 is based on adaptive thermal comfort, and that measures you against a target that is a movable thing. So it's based on the outside, what the average running mean of the outside temperature is. So as we look to future weather files and that temperature increases, our target rises gently. So it's still attainable when you look at criterion 1 tests going forward into the future. It doesn't immediately make it impossible. What makes it hard is the nighttime 26 fixed threshold that we have in TM59. Now, I'm in the privileged position of knowing, because I'm on the TM59 committee, that we are looking into that, and there is research being undertaken at the moment, because the basis for that 26-degree nighttime threshold is like light, scant evidence based on like 8 people in China who slept in pajamas under wool blankets in the 1970s, something along those lines. So there is more research to be done about actually how we are comfortable at night and whether we can adapt more, and whether running against the more adaptive nighttime criteria might be more pragmatic and sensible and actually helpful, particularly when it's usually the nighttime hours that kick out London assessments, if that's what you're, yeah. It's usually nighttime where you hit a wall and you can't make it pass. So long way round, and yes, a discussion. But I think it'll take a while because academic research takes a while to sort of formulate, and then it has to be tested. But potentially there'll be an update to TM59 in a year or two that will look at that.
Work in progress.
Hmm?
Work in progress.
Work in progress. Yeah, sorry, it's not going to be immediate though. And who knows whether Part L will then adopt it as well.
Just a bit conscious of time, so do we want to take maybe a last question? Maybe Kartik, you get it? Just for the privilege of knowing your name.
Kartik from PRP Architects. Elaborate a little bit on your adaptive comfort explanation. The criterion one, which is adaptive method, applies for both day and night. So because it's more related to seasonal aspects and running mean or for day temperatures. So considering that the night time is something different, or having a different sort of adaptive comfort, will also be a kind of a conflict.
Sorry,
do you understand the question? Yes. Yeah. So can we use the adaptive thermal comfort model if at night we're not using natural ventilation? So if you're using mechanical ventilation or comfort cooling at night, but you're using opening windows at the day, so you've got a hybrid use. Can you still use the adaptive thermal comfort model in TM59? Is that right? Is that your question?
Well, there are two questions. The first one is that the adaptive method applies to both day and night time, so it's not different. The criterion one is just because based on seasonal aspects and also running mean daily temperatures. So you can't really differentiate between day and night in criterion one.
I agree.
Then
the government in the FAQs that they published, they did a sneaky thing, I think, and said because it says for the adaptive thermal comfort model, if your building is predominantly naturally ventilated,
correct.
And they said, well, if it's still predominantly naturally ventilated, if you don't use natural ventilation at night. So if you shut the windows at night and use mechanical ventilation to overcome the noise problems, they say you can still use the adaptive thermal comfort model.
Absolutely. So that's another gap. But if it is a fixed method on criterion 2, that kind of indicates that it's mechanically ventilated because it's a fixed method and it's not naturally ventilated.
Exactly.
Space.
And then you'd have to use the fixed method in the daytime as well, and then you're totally.
So there is no sort of let's say leeway in doing an assessment where you say that all the other spaces except bedroom are predominantly naturally ventilated, but bedrooms can be mechanically or comfort cooled.
You can specify your bedrooms separately. I mean, the TM59 will allow you to say your bedrooms are mechanically ventilated and your living rooms are naturally ventilated. You can do it that way.
I don't think that there is a method for that right now. Yeah. No, it allows to model it as naturally ventilated and mechanical ventilated. I'm not sure that if it allows some space to be mechanical and some space to be naturally ventilated, because the level you're talking. I think the background is that we're talking about a building, not a space. So the building is naturally ventilated, not the spaces as such. So when you're defining it, it's more at the building level rather than space level. That's how I've understood it. Unless we are defining unless we are defining that out of a building there are certain type of spaces which are mechanically and some are mechanical ventilated or cooled, and some are naturally ventilated.
It's not the way it's designed to work. It would be odd to have a home that was half mechanically ventilated and half not. I don't think it comes up very often.
I think, sorry, if we can wrap up online, and then we can stay here as well. So thank you everybody who came here and online, and thank you very much for your presentations. Yeah, that's a wrap up.